Please give a warm welcome to Dr. Phil Root.
Good morning. There are many ways of viewing DARPA, and you've heard some of them throughout your day yesterday and your morning so far today. One way of viewing DARPA is as a collection of innovators. Greg Wickhop, for example, finding the state of the art and surfing along that frontier of science and technology, particularly aimed for national security. Another way of viewing DARPA is as a collection of truth tellers. You heard that in the panel on field robotics yesterday, where it's a technology-informed conversation about what can and cannot be done in the field of field robotics. I'd like to provide you another perspective on DARPA's unique role, and that is of paradigm disruptors. Let me explain. The military operates within certain paradigms, and DARPA's role, not only opportunity, but really responsibility, is to build out some of those paradigms, but also challenge them. Stealth is one example. So there was a time when the paradigm for the Air Force was to seek aircraft that flew faster and higher to evade threats. And DARPA invested in materials that brought about stealth as a different paradigm, saying, what if we were just invisible? Different paradigm, we fly lower, we fly slower, we can accomplish the same mission, solve the same problem, to use Haumeier speak, but do it in a different way. We're in the age of the birth of, or the genesis of a different paradigm of warfare, of jointly composing effects on the battlefield. That is something that we aspired to for many ages, and now we believe that the time is now. This is such a vision where the forces working, the services working together are actually working as services. The play on words is the capital S services, Army, Navy, Air Force, Marines, Space Force, are serving each other in ways that were undone or unperformed in the past. So imagine the Army providing a service to the Air Force by creating opening an air corridor, for example. We consider this multi-domain operations. This is a new paradigm of warfare within the US, our partners, and our allies. And so DARPA's role here is to, one, build out this existing paradigm, but also to hedge against it and wonder what else, what other ways, what other paradigms we could explore. What I'm hoping you're thinking at this point is, how do I help? At this point in your time here, how do I help? And what I want to do is explain some ways that we're thinking about this, but also solicit your assistance in doing so. And so as we look at this new paradigm, we see opportunities for new forms of sensing, planning, communications. My animation here highlights the central role of the human decision maker, and that is incredibly challenging within this new paradigm, given the significant distance from, potential distance from a human decision maker to those battlefield effects. How do we ensure that we respect the centrality of a human decision maker? Many opportunities for new innovation, but the first thing that we do when looking for breakthroughs, and so the first thing I'd encourage you to do is to be more concrete. So within this paradigm, let's look at a smaller example, a smaller use case. Consider the defense of an aircraft carrier against simultaneous threats arriving potentially from different directions, launched from different platforms. Here is an opportunity for us to build out that same paradigm of jointly composing sensing, communications, planning, but in a much smaller and tractable use case here, the defense of the 3,000 to 5,000 sailors on an aircraft carrier. You can imagine now the challenges of making decisions very quickly, and again, putting the human in the center of that decision cycle. As we look at even this concrete use case, you can see there are multiple opportunities for tech innovation. And as we look at what DARPA should do versus others, we look for what is the most compelling and dare say disruptive concept that would change this paradigm. Does that help you think more concretely? I'd like to invite one of our program managers to the stage to explain how he views some of the opportunities within this tech space.
Okay, so we're going to walk through a couple examples where you'll have an opportunity to think through paradigm changes or very different ways to approach problems. And as I go through these examples, I'm primarily speaking to three parts of our audience. Those of you who have never done work with DARPA before, I hope that you'll be able to see how we approach problems differently so that you can write more compelling proposals to us and approach us with problems or solutions to problems in a way that's compelling. I'd also like to speak to those who have done work with DARPA before and want to keep doing work with us in the same way. And then the third part of our audience that I'd like to talk to is really all of you, which is those of you who should consider becoming a program manager yourself. And it's my hope that you can that this will inspire you to say, hey, I can think like this, and I can make an impact to do this. So we'll use this example of the aircraft carrier. It's a very simple example, but if you think about all the steps that need to happen in order to defend the aircraft carrier from this threat, there's a lot of complex things that you have to do. You have to sense your environment. You have to know that the threat is coming and that threat is moving fast. You have to plan what course of action you're going to take, and you don't have a lot of time to do the planning, and so you have to plan quickly. You most likely have to communicate with partners on how to address the threat. And in many cases, our adversaries are adapting, and they're adapting fast, and so we also need to adapt, sometimes in real time. And then, of course, autonomy has a role, and testing has a role. As sort of kind of an interesting side note, I practiced this talk at my children's career day, junior high school, and I showed them the aircraft carrier example, and I solicited some innovative ways to think, and I got some interesting answers. I said, well, maybe the aircraft carrier can dodge, right? Maybe the aircraft carrier can shoot it down, right? One kid said, why don't we do a cyber attack so they couldn't shoot the missiles in the first place? This is a junior high school kid, right? So these are the types of things of approaching the problem differently. You know, if junior high school kids can do it, you guys can do it too, right? All right, so let's get into these examples. And as I go through these examples, I want you to look for two things. I want you to look for the answers to two of the Heilmar catechisms. What are we trying to do? How is it done today? And then I'm going to explicitly identify how we're approaching this problem differently, how we're challenging the paradigm of how it's done today. So let's do the first example. This is an example from a program called Ocean of Things, and John Watterson's in the audience somewhere, and he's the program manager for this effort. The problem that we're trying to solve here is we need to have an awareness of our environment. We need to sense the missile, but we also need to sense the environment, right? And the ocean environment is a particularly challenging environment. And traditionally what we do in sensing the ocean environment is we build large, expensive satellites and expensive sensors that we put in the water column. And these large, expensive satellites, for example, can sense remotely, and they can do a good job at sensing things like the temperature of the water and the cloud cover and that sort of thing. But they can't sense things like currents directly, right? And so John approached this problem very differently. He said, we don't need large, expensive sensors. What if we go the opposite direction? What if instead of large, expensive sensors billion-dollar platforms, why don't we take all of the technology that has been developed for the cell phone industry and make the least expensive sensor we can possibly make, and let's just throw a bunch of them in the water. And I don't know if we have any fast counters in here, if you've already counted those dots or not, but I think, I could be wrong, but I think there's about 1,000 there. And these are real data, right? So, and this is only one of many deployments that John did over the course of this program where he took these sensors, and you can see a picture of the sensor there in the bottom right, where he took 1,000 of them in this case, threw them in the ocean, and the currents just appeared, right? We could now sense the currents in a way that we could never do before with these large platforms. And so you can see by approaching the sensing problem in a very different way, we have this great innovation and this great new capability. Okay, let's move on to planning. So this is just a picture from an encyclopedia, but what we're doing with planning is challenging. So how do we do this today? Today, when we have to plan for a complex operation, we have a bunch of people sitting around a table. We call it BOGSAT, a bunch of guys sitting around a table. And we have them use their experience, their human experience, to take this infinite possibilities of how you could execute an operational plan and narrow it down to 5 courses of action. We call them COAs. So humans are uniquely capable of doing this, of sort of taking infinite options and narrowing it down to ones that are really compelling. And this has worked well for us since Sun Tzu, or maybe earlier, right? And we're very good at it. We're now at a very unique point of time where we're starting to model the battle space. And the way that we're modeling the battle space now is saying, oh, we need really high fidelity. We need to make sure the logistics supply chains are right. We need to make sure the environment is modeled properly. We need to make sure that the probabilities of our missiles and our weapons are accurately captured so that we can make good decisions about operational planning. That's all good. We simultaneously have this effect where I can say today that in the strategic space, strategic games, machines are beating humans, okay? We can now say that machines are beating humans in all games. I think Atari was one of the last holdouts there. And so we're not using machines right now in our operational planning except in this high fidelity way. The problem with modeling with high fidelity is they go slow. The more fidelity you put into the model, the slower it runs. And so the way machines beat humans today is they use artificial intelligence, not real intelligence, artificial intelligence. It's fake. And the way it fakes it is it just runs many, many, many iterations, okay? You can't run many, many, many iterations if you're focused on fidelity. So we're approaching this problem differently. We're saying, let's not focus on fidelity. Let's focus on speed. Let's take these high fidelity models. Let's abstract them to a level that we can run fast. I'm not going to give you the exact numbers, but very fast. And then let's develop lots and lots of courses of action, many orders magnitude greater than 5, I'll just say. And then let's whittle those courses of action down to a small number, put them back into the high fidelity model, put human eyeballs on them, and say, does this resonate with our intuition or not? This is a program called Scepter. We've kicked this off, and the hope is that we can use these tools to better enable our human planners in making more compelling operational plans and to avoid the inevitable biases that we humans put into those operational plans. Okay, so again, a different way of how to look at the problem. All right, let's move on to resilient communications. I tell my wife that part of my job is making radios work the way people think that they already work from the movies. I think in the latest Top Gun movie, Tom Cruise jumped in a Russian jet and was able to communicate to the U.S.
Yeah, right.
It doesn't work that way.
Yeah.
So this idea of getting radios to talk to each other is actually very complex, especially whenever you say, hey, we need to make sure they're encrypted, we need to make sure they're resilient. And so we have this proliferation of radios. Some radios are better for the ground, some radios are better for the air, some radios are better for different CONOPs, or concept of operations. So because we have all these different communications, the traditional way of thinking about this problem is when we say, well, let's have one node in the network that has all of the radios, and we'll just have all the communication go through that node, do a translation, and push it out to the different. It's a very centralized kind of spoke and hub type way to approach the problem. And that has worked for us for a variety of missions. What we're doing on this project is we're saying, well, what if we have not one hub and spoke type model where our adversaries could just attack the hub and then the whole thing falls apart? What if instead we put a bunch of miniature, we'll call them gateways, throughout the network, and let these miniature gateways do translation and pass it on? And you can see how now we're very resilient, right? Because if one node in the network gets taken out either by jamming or some other way, we still have the rest of the capability in our network. So now we're simultaneously solving the problem of interoperability, and we're increasing our resiliency, and we're imposing complexity on our adversary. Think for a moment, if you put yourself in the shoes of an adversary trying to jam a network like this, well, which radio should I jam? And okay, do I have to jam a new radio now, different frequency, different waveform? So this idea of imposing complexity. All with a very simple way of just looking at the problem just slightly differently with these resilient communications. Okay. All right, let's stick with communications for a little while, but let's add some learning to it. So this is a program where we were asking ourselves the question, how can we better combat interference? And in this case, I'm just going to say this is intentional interference. Sometimes we call it jamming. So in this diagram here, we have two blue nodes at the bottom. The one that looks like a circle is sort of the sender, and the one that looks like a jet is the receiver. And this is an animation. Let's see if it's playing. So what you'll see here is that blue jet is flying north towards this large red circle. And that red circle represents the area in which they are jamming the communications. And if you look at the baseline plot, you can see that the communications were going at about a megabit per second, and then once it entered the jamming area, the communications dropped to 0. Okay, so that's the problem that we're trying to solve. The traditional way of doing this is saying, hey, we want communications with high bandwidth, we want communications with low latency and high data rate, and let's just power through that. We decided to look at the problem a little bit differently. Okay, we said rather than try to punch through with a fancy waveform or with high data rate, what if we could guarantee just a few golden bits of information? Let's say 1 bit of information, right? And we could guarantee just a bit of information. What could we do with that? And what we're showing on the bottom here is with 1 bit of information, when the aircraft is within the influence of the jammer, it can say, hey, I lost communications. Or, hey, I got communications, right? It's the bit, right? And with that, we can communicate back to the sender when I'm getting communications, when I'm not getting communications, and then we can throw on a Q learner to it. And the Q learner can say, hey, you tend to lose communications at this place. Let me try to adjust my radio parameters to see if me, the sender, can adjust my radio parameters to help you punch through that interference. And you can see that after it's done a couple cycles, if you look at the lower plot, you can see how it's experimenting with different radio parameters. And after just 3 cycles, it has learned to proactively adjust those parameters to push through the interference. Again, looking at the problem in a very different way, and having profound impacts on the performance. Okay, now let's stick with some learning and move into autonomy. So I mentioned this a little bit at my lightning talk yesterday, but I wanted to show you a video of this. So what we're doing here is we have some quadcopters, and we're playing that capture the flag game. And these quadcopters have mines that they can lay, and the objective of these quadcopters is to get the other person's flag that's in either the red area or the blue area and bring it back to their own area. And you can see these quadcopters flying around. We've overlaid some of the logic there that is fundamentally controlling the behaviors here. So how are we looking at this problem differently, and how and how are we having success with this? Okay, this is a true story. I'm going to change the names to protect the innocent. But I was having a conversation with one of our performers, and I said, hey, we had an aircraft, we had an autonomous aircraft in there, and I said, hey, what's special about this aircraft? Can anybody fly it? And they said, oh yeah, this is kind of an off-the-shelf aircraft. Anyone with a pilot's license can fly this thing. I said, okay, and you're putting some autonomy on that, right? I'll say, oh yeah, we're putting autonomy on it. But once you have autonomy on it, you need one of us experts to fly it. I said, guys, that's not autonomy, right? We want to go the other way. So in a lot of the cases, while we're pushing on this autonomy tends to do tasks very well, but it tends to be a little bit more brittle, right? And so the way that we're doing it differently here is that rather than have sort of heuristic autonomy functions, heuristic autonomy graphs, we took these heuristic autonomy graphs as a whole, and let's say you have a command of capture the flag, and it would know exactly the steps that it needs to do to go get the flag and bring it back. Rather than treating those as a whole, we said, why don't we break these up into little pieces of the graph, right? Little pieces of the functions that we want to do, and then let's have a learner learn those pieces and more adaptively react to changing situations. And in this way, we're able to not only make autonomy we're able to make autonomy more robust, right? By looking at the problem in a different way. And by the way, there's a tendency in the community to think about autonomy and machine learning as the same thing. They're not the same thing. But when we do combine real autonomy with real learning, you can have some profound impacts to the success of these systems. Okay. So let's move on to this next one. So I also mentioned this one a little bit in the lightning talk yesterday. But this idea of doing a distributed system of system, composing distributed effects in the battlefield, not only with manned platforms, but with unmanned platforms. This results in tremendous challenges. Because the unmanned platforms need to not only address the challenges of autonomy that I already mentioned, but it needs to operate in real and complex environments. In this particular project, we had a lot of R&D systems. We had a lot of what I'll call low TRL systems, and we're trying to interact with very high TRL, technical readiness level systems that had people on them, right? And people are kind of the best autonomous unit. And having these things interact was extremely challenging. And it's nice to sort of to think that we can solve these problems in a comfortable office or in a comfortable laboratory space, thinking about comfortable things, but the environment will kick your butt every single time. And so it's important that we put these systems in the field. It's important that we approach these systems in such a way that we can test them and show that they are really resilient and that they can really do the job. So how is this done today? It's done with sort of this or how has it been attempted in the past, I should say, because this actually isn't done today. And in a lot of cases, we have DARPA programs that are addressing things that just literally haven't been done. And this is an example of it, or not, even though it's been attempted, never been done. And so the way it's been attempted in the past is to have some strict protocols. And in this particular case, we needed to ensure that we have resilient communications and allow that adaptive behavior that I talked about earlier. And we're able to show that we can interact with manned platforms and unmanned systems and show that we can produce real effects, real meaningful effects, and not risk manned platforms. One of the challenges with transitioning technologies like this is that when we're talking about real operations and in real theaters, there's a comfort level in what we have done in the past, right? There's a comfort level of saying, I know this works, I know there's a person on there, I trust that person. And so not only do we have to overcome the technical challenges, but we also have to overcome these comfort level things with our warfighters. And they are right to push back on us, right? And so this idea of having a healthy discussion, a healthy push-pull, is part of the job. Okay, so hopefully I was able to share with you a couple examples, a couple of specific examples. Hopefully you're able to see H1 and H2 in those examples, and hopefully I was able to illustrate a couple of different ways that we were able to challenge these paradigms in the sensing, planning, communicating, learning and autonomy, and testing. And I think we can.
Yeah. So, thank you.
Yeah.
So we've talked about disrupting paradigms. One of the paradigms for giving a presentation like this is that while we wait for your questions to come, that we have some questions that we've discussed before. I'm going to disrupt that paradigm by asking questions that occurred to me while you talk, because you never quite know what Aaron's going to say, and so I never quite know what my reaction is going to be. You've worked in communications programs across a number of different domains. Are there any domains of communication, or what ways are you thinking about communications that you think has the most opportunity to actually deliver on the challenges of making radios that work the way that we think they do?
Mm-hmm. Great question, and there's a lot of people thinking very hard about this question. You may have heard about a lot of big efforts thinking about that. Ironically, so this is Aaron's opinion, raw and whatnot. But ironically, I think that perhaps the best way to ensure reliable communications is to use communications as little as possible, right? Yeah. I think we are addicted to data. Yeah. We are addicted to communicating. And I think that addiction, now, communication is essential for coordinated action. We have to do it. But do we need high resolution video such that it's sometimes called a 1,000-mile screwdriver? Do we need that 1,000-mile screwdriver? I don't think so. And I think it actually hurts the reliability of the data that you actually need if you attempt it.
Next question, you discussed in passing imposing complexity, and you offered several domains in communications, in planning, and autonomy. Each of those have tactical to strategic opportunities for imposing complexity. I was wondering if you could zoom out and say, rather than just the technical pieces, are there domains where you think they're ripe for imposing complexity, or is that the right way to even think about it?
No. So I think there are certainly domains in which we can impose complexity, and one of the domains that's fairly challenging, and there has been some unclassified and open discussions about this from even Stratcom Actual, about how we live in a different world now from the perspective of deterrence. I mean, it used to be, if you watch our favorite 80s movies, right? It was the bad Russians against the good United States, and we were trying to ensure that we don't destroy the world with nuclear weapons, right? And that resulted in mutually assured destruction. That doctrine, it's really a hypothesis. It's never been proven, thankfully. It's never been proven. But we're now in a situation where we have multiple threat concerns, multiple threat vectors from not just one nation state, but multiple nation states, terrorist organizations, insider threat. We have all now. How do we now deter bad actors when we have that complex number of adversaries and a globalized world? Right.
Admiral Paparo mentioned integrated deterrence, and he mentioned more than just military. He mentioned diplomatic, information, military, and economic. Thoughts of where innovation or new forms of deterrence? You've talked about the three-body problem as a new challenge when we think about deterrence, much less the interconnected, globally connected world. Yeah. Thoughts on what a new model of deterrence might look like, particularly a three-body problem?
Yeah, I think. So I actually have more thoughts than we probably want to share here on that. But let me just pose, maybe not an answer to your question, but maybe another question. If you think about the way different people might be aggressive, and I'm going to use a really simple example that is actually really instructive to think about. So let's think about the game of chess and the game of Go, right? So I'm a chess player, and the game of chess is all about, you have a very clear objective, that's your king. And it's all about finding pressure points and applying those pressure points in the right spot to get your adversary to either not be able to advance their own objectives or be compelled to respond to your objectives. That's very much like the traditional Cold War two-body problem. Yeah. If you look at the game of Go is a very different kind of game. And the game of Go is all about surrounding. It's all about subtlety. It's a very big board compared to chess. Right. It's about a position. It's about switching places. And the game of Go, you want to surround. If you look at China's Belt and Road Initiative, that's very Go-ish, right? Yeah. If you look at Russia's war in Ukraine, that's very chess-ish. Yeah. How can we play Go and chess simultaneously in doing this
at speed?
At speed, that's right, at speed.
As you were thinking about the planning program that you presented, you drew lessons from Centaur chess. Any you care to share, since you outed yourself as a chess player yourself, but you also often say you're not as good as Centaur players?
Yeah. So chess is a really interesting example in technology for a number of reasons, not only deterrence, but also for artificial intelligence. Chess was kind of the first big game to fall to AI, and I actually remember as a young chess player watching Deep Blue beat Kasparov. And Kasparov has since written a lot of articles about that. And if you watch chess through that arc and its interaction with technology, it started with, machines have no place here. They're kind of comical. We dismiss them. Chess players would even say, oh, that looks like a machine move, to kind of like insult you.
Denigrate it.
Yeah. And then it beat Kasparov, right? And that was with the first wave of AI. And we talked about the 3 waves of AI yesterday. And that was with an expert system, right? And then we go into, okay, chess is a player now. But with that first wave of AI, we were able to show that the AI plus the human were better than either the AI or the human. And that was an interesting place to be. Now with the second wave of AI, we've shown that with a closed game like chess, the AI is just better. It's just better than all humans, right? And now the best players train with AI. So you can kind of see that arc. Circling back to the planning, will we follow a similar arc in warfare planning? Maybe. I think we're starting with, hey, that's silly, that's silly toy stuff. I think we'll easily get to the point where we're saying, actually, it's not silly, it's very useful. I think we'll easily get to the point where humans plus AI will be more powerful than AI or humans alone. I'm actually not sure if we'll ever go to that third step where AI is always better. I personally think we never will. Yeah. But, we'll have to see.
We're not there yet to know whether we can test it. You mentioned the difference between AI and autonomy, because planning is one thing, but then implementing it, in the cases you gave, it'd be implemented by humans with autonomy. Yeah. Or it could be implemented by machines with some autonomy. Autonomy is not a magical capability, it's a trust. You're trusting humans, or you're trusting a machine to go implement some part of the plan. Do you have what are your feelings on limits of that autonomy for machines? Because I think the way I view autonomy is that trust. Yeah. Do you think there's a limit to the degree of trust that we'll provide to machines?
Yeah, I think so. I actually feel you're a better expert on autonomy than I am, so you might want to share more of your thoughts on that. But I think that I think that there are we should be responsible about this, but there's also devious things that we can kind of do for this. So for instance, we don't recognize how much trust we put in autonomy today. Yeah. Right? Our cell phones are constantly pinging towers without us telling them to do it. And is there a pop-up window asking us every time, hey, is it okay if I transmit some RF energy? Yeah. And we don't do that. I mean, and so the devious thing would be to just say, make the autonomy work and don't even ask, right? And if it really works, people won't even want to ask. Yeah. And so you sort of go around that question of trust. However, trust will always be a factor in talking about things like making warfare decisions, those hard decisions.
Yeah.
And I think that although autonomy may be able to make those hard decisions faster, arguably better, it's probably not ethical for them to do it. I think that we need to have that personal connection to say, me as a person, I'm making this hard decision on the battlefield. I think
it's
that's
that agency.
necessary.
That person has the agency
Yeah.
to make those decisions with significant consequences. We refer to those as ethical, but there are also legal consequences associated with them.
Yeah.
So it goes, in my mind, to some of the challenges of testing. We can view it as a technical conversation of what is the limits of autonomy beyond which we wouldn't trust it. But I think the trusting comes from testing, and that's an often trod road to talk about trust and testing together. But I think now's the time for us to think differently about the way we test our autonomous systems, because we don't scale particularly well.
Right.
So we need some way of helping the developers and the autonomous systems improve. We've talked through a couple questions that we just had from the audience. One is, how do you get to trusted field testing? Can you test enough to be confident in our complex joint battle space? I'll start if you don't mind.
Yeah. Oh, yeah.
I think that the second question, can you test enough to be confident in our complex joint battle space? I don't think that's an answer that we can answer. Our responsibilities is to develop capability. The question that we pose, this is really a question for operators, decision makers. To what degree are they willing to trust? And I had a program, Squad X program, where we're building AI and robotics for urban operations. It's the crucible of warfare. It's fascinating because in field robotics applied to urban warfare, if you're off by a foot, you're irrelevant. So if you're a robotic system and you are 1 foot ahead of the cover that a building provides, you're a target. If you're 1 foot back, you're irrelevant because you can't see anything. So that degree of localization precision is not currently possible. We didn't realize that was one of the tech innovations that we needed to start with, for example. But working in that space, in that crucible of warfare, in the urban environment, I got to work with a lot of Marines. And so I posed this question to them, and I wish they were here because their answer is pretty concise, as is the best answers, particularly those from Marines. And the Marine Staff Sergeant said, "Sir, I trust stuff that works." He used slightly different words. It was actually more concise and impactful. I trust stuff that works, and I think that is the path to testing autonomy. We have to show it works. The dual of that is we have to show when it's brittle, and that is a Pareto front that's hard to characterize. If we know it's brittle, we can fix it. The problem is we don't know in what areas it's brittle. It goes to a larger conversation about the legal, moral, ethical decision making. Humans have the agency to make decisions. When we use autonomy, we're asking them to make decisions about trust in capabilities at a point where they don't know where it's brittle. Mm-hmm. And so we're actually asking them to make impossible decisions, I fear. And so I think there's an opportunity for innovation in testing so we could characterize performance, really calibrate trust, I think is a helpful concept. So we can calibrate trust so someone could actually trust stuff that works, particularly in high-risk environments.
One other thought along those lines about can you test enough to trust it? Implied in that message is sort of a paradigm, I would argue, mm-hmm. where a lot of times we think about defense like a castle wall. We want it to be, mm-hmm. we want it to be big, we want it to be thick, we want it to be stable, we want to be able to point to it. And this idea of that sort of stability gives us comfort. And it gives us comfort to know that those castle walls are manned, there's people on them, so I can fire that person if they do something wrong. So that sort of stationary stability is a paradigm that I think is throughout the DoD.
Yeah.
And I'm not saying it's necessarily wrong. It's just identifying as a paradigm. There are other paradigms, and I'm not going to say this one is correct, but there are other paradigms for stability, and that's dynamic stability, right? Yeah. A bicycle is a perfect example of this, right? If you're stationary on a bicycle, you're anything but stable. But if you're dynamically moving, right, at the right speed for the environment, then you are the most stable. So this idea of composing joint effects in a battle space, we're actually asking them to say, leave your castle and ride a whole bunch of bicycles. I don't know if it really fits, but it's a different kind of stability.
While playing chess and go.
Yeah, while playing chess and go.
Next question. When you're sensing in the ocean, what are the environmental impacts? I'm going to hand that to you.
Oh, thank you.
Talking about getting fired.
Yeah, that's right. So we do a lot of testing in the ocean, and it's actually a pretty exciting part of the job, actually, is to go to beautiful places of the world, go out and go into the ocean. And I actually remember the first time I was doing a DARPA test at sea on the East Coast, and I was looking to the west and seeing the sunset over water. And it occurred to me, I am really far away from land, right? So it's exciting to get out into the wild and to test these technologies, and these technologies really benefit from going into the wild. At the same time, we are compliant with all of the laws, environmental laws like the Marine Mammal Protection Act and all of the laws, to include not only debris, like Ocean of Things might have concerns about debris, but also acoustic energy in addressing that. And it's a lot of work to do it, but we do the work. Right, and we show compliance, and oftentimes we partner with Navy and other partners to help with that compliance. And there's a bunch of systems and a bunch of things we need to do in order to show compliance. But all of the work that we do in this space is compliant with all of the applicable laws.
Next question: for communications, how much of the challenge is technical, electronic, wireless tech, et cetera, versus social science, perception, et cetera? And if you think that one's easy, how do we position research to address this?
Do you want to go for it, or I mean, that's a great question. No, you want to okay.
I've got the clicker, so you go for it.
So I think it's a very astute question, right? It's an astute question because in most cases, it's not just technology. I think it would be a mistake to think that you can come up with the most brilliant waveform and that will solve everybody's problems, because especially in the, I'm going to brag about the Strategic Technologies Office. I feel like especially in the Strategic Technologies Office, we need to look at the whole problem. Mm-hmm. We need to look at not only the technical part, but the human part, the lifetime, the concept of operations, how it will be employed, how it will be recovered. We have to look at the whole problem. Yeah. To include the social science. Now, the social sciences are a little bit harder to get at because they're squishy. Metrics are very important to us. We need metrics as sort of our guiding direction to ensure that we're making progress against the technology. When we get into social sciences, at least for me, it's a little bit harder to get your fingers around that. But it's an astute question, and it's something that we talk about a lot in the building. Yeah. And we talk a lot about how do we come up with a metric to measure this impact.
Yeah, and it's as we talk about, one of my thoughts is we talk about imposing complexity. Complexity, by its nature, escapes simple metrics. Social science is hard to find tractable research to the question because it's hard to simplify the complexities of social science. We're non-deterministic individuals. And so I do think that now is the time for us to conduct that kind of work, because calibrating trust is a human dynamic. And if we want to impose complexity, if we as a nation with our partners and allies have the ability to leverage complexity, particularly within human decision-making, in a trusted, calibrated way, I think we have a significant advantage. So there's real opportunities. And one of the hopes is if you have any thoughts out there, you'll meet us for coffee momentarily and let us know what could be done to help really impose complexity by leveraging the complexity of social science. Last question. What do you think are ripe areas for challenging current paradigms? I think we've reached our max use of paradigm, so I ask you not only answer that question, but not use the P word.
Okay. Well, we already talked about some. We talked about deterrence as one. Yeah. And I think you're leading out on challenging the office on other areas. So we have what we'll call the classic STO problems of radar systems and acoustic systems and maritime systems and ground systems, communications. But there's a lot more, right? So deterrence would be one. We talked about economic factors. We're even starting to talk about things outside of Earth orbit, right? So, or at least low Earth orbit, or even geo. So there's, I think we're only limited by our creativity. And if you see an area that we're missing, tell us.
Yeah. And I'll end the way that Aaron started. Love to reach out for you to consider joining DARPA in this search, consider proposing, consider letting us know what areas of exploitation are ready now, ripe for exploitation. But also, if you're thinking about now is the time for you to join the team, would love to talk to you. So thank you in advance for the conversations we'll have at the next break. Thanks.